Dr. Chen. Hi everyone. How's it going with the last week? Welcome to our 10th discussion. So this week our topic is the lecture 13, atmosphere ocean coupling, the WRF FVCOM coupling model. So this is our last lecture of the whole semester. So as usual, so we may first let everyone to raise questions about this lecture. So after all the questions have been raised, so we will answer all of them one by one, okay? So who's first?
I will do first. Okay. I can't share my screen, so
Please try again. I just open the permission.
okay. In the lecture, the ocean model gives some SST data to WRF, the atmosphere model, and I want to know how the surface temperature at the land domain are handled. It is just updated by interpolation by using a weight, or there is something other method. So, and I have one more question about the initialized part of coupling FVCOM and WRF. And I want to know why it is necessary to calculate the initial condition of FVCOM by using WRF data. That's all my question.
Okay, thank you so
Thanks.
much. Next one.
Okay, I will share my screen. My question is here. So I understand that WAF and FFCOM coupling model calculate the wind max speed to equation of the Bister and Muir equation, and it used the sea surface temperature as TS. So in the result, it cannot consider the surface water temperature steps. So I think in TS, how we replace with the depth average temperature, only surface temperature can better result is my question.
Okay, thank you. Next one.
I have a question. Can I share my screen?
Yes, please.
Okay. I have a question about the physical process of storms. From physical process of storms. When a storm moves northward, I learned that the cyclonic wind rotation occurs on the left side, and while anticlonic wind rotation occurs the right side. And I also learned that the inertial resonance tends to occur primarily on the right side of storm. Why does inertial resonance mainly occur on the right side of storm? And since the wind is generally stronger on the right side, does that lead to stronger overlaying in that regions as well? Is my question. Thank you.
Thank you.
Hello, more?
Okay,
You
I show
you
I,
you
I,
mute
sh
yourself.
Yeah.
I share my screen. Can you see?
Yes.
Okay. The maximum wind equation by Bister and Emmanuel does not consider the effects of the cold wave caused by mixing or convection within a storm. And I understand that vertical mixing in the upper ocean caused by strong winds in the storm is important for predicting storm intensity, and that that the cold wave should be considered. But about its impact on the storm's track, the mechanism doesn't quite make sense to me. That's my question.
Thank you.
Hello, more question?
I have a question. Can I share my screen?
Yes,
Okay.
please.
I think it is similar to Minu's question. Given the results shown here, why is inertial resonance response more evident on the right-hand side of the storm? Is this primarily due to the alignment of wind rotation direction with the correlative factor, or there are other contributing factors such as storm structure or bathymetry? This is my question.
Okay, thank you.
Okay, yeah, that's similar to the second question.
Yeah.
So is there any other question? Okay, so if no, so let's start with answer the questions one by one.
Yeah, I think Dr. Lee can answer the most of the question. Lee, you can answer if you need me to add more, can add more for each question. Okay. For first question, definitely you are expert, you can answer.
Oh, I will try my best. So can you see my screen? So first question is from Yunji Song. So the question is for the transferring data from WRF to from ocean model to the meteorology WRF about the SST. So when we do the coupling between the FVCOM and the WRF, we transfer the SST from the ocean part to the atmosphere as the air-sea interface. So Yunji's question is good that when we do the transfer of SST, so we did some special interpolation for the SST because first, FVCOM and the WRF has different grades. So FVCOM is triangle mesh and the WRF is structure grade. So we need to find a triangle interpolation to SST from the triangle mesh to the WRF grade. And the second thing is about the land and the sea distribution. So near the coastal region, so we need to make sure that we do not include all the surface data on land. So in WRF for the variable SST, although its name is sea surface temperature, however, it has all the values on both ocean and land. So on the land, it means the land surface temperature, and on the ocean, it means the sea surface temperature. So when we transfer the data, we need to remove all the SST on land. So because if we include that SST data, so it makes our data very strange. So that is why we only consider the data over the ocean. So we got the SST from the FVCOM, so we will just interpolate the data onto the ocean part of the WRF. So that is the first question.
Yeah, I think I can add a little bit of first question. That's the answer, this company only do the ocean part, not include the land, okay? Because the land is there, so this dynamics is completely different for ocean. We talk about air sea coupling, most of the ocean and atmosphere. Wolf had a defined, file. He can identify where his cell was on land or cell was on the water. So that's what ENSF, the coupler, is really working on to get, just like Dr. Lee said, they have a two-way, integration. One way is from the wharf to the ocean. This part be careful, only the ocean part into the FVCOM, FVCOM only the ocean part. But if you have a wet dry pond, you have to consider about the land part, but not for this coating right now. They don't I don't think they consider that. But if I said it wrong, Dr. Lee can correct me. But the ocean part to atmosphere is easy because it's only have the ocean data, SAT data. All right, most of it just land to the ocean, but they have a program like Dr. Lee said, for the wharf to the FVCOM, the ENSF program can convert the structured grade to unstructured grade. For FVCOM to the wharf, they go from unstructured grade to the structured grade. But they have a different kind of integration program inside of ENSF, right? So recently they had a very conservative interpretation for many methods. I think it's Dr. Lee was just choose the one method, more popular method used in the coding. Okay. Yeah.
So, Professor Chen, what if there's a tidal flat?
Well, we should tie the flat. Oh, tie the flat there because we assume this coupling right now, if I said it wrong, Dr. Lee can correct me. We didn't do the coupling on the tether flat because we didn't consider the interpretation program, the ENSF for dry and wet pond, right? Dr. Lee said correctly,
Yes.
right? So we only consider everything in the water. But if your FVCOM running have a tidal flooding there, so if the water is wet, they got a temperature, so then the interpretation to warp. Right? Because they have a boundary over there. But for the wharf to FVCOM, you don't know what's the land is the water is really difficult. That's why we assume the couple model, wet dry pond the land, the temperature be advected from the coast region. So you got a tidal flooding going back. You have AC interaction for wet part, wet pond intervention. So then the water on the land, just the more temperature is really, it's driving by wharf temperature, that's the land. So then I have a water advection come from wet pond. But in the coupling, I don't think we do that. Do I say it correctly, Lee?
Yes, that's correct.
Yeah.
So actually, the Incheon airport,
Yeah.
do you remember the Yeongjong Island, the Incheon airport?
Yeah.
They have a serious problem of sea fog.
Mm-hmm.
And research question would be like, what is the effect of tidal flat on the sea fog or up to the atmosphere?
Yeah. If you want to do that, that's the interesting is, so C4 water there, you have the atmospheric model. So this means you have a wetland, you can how the evaporation, a lot of things going on for the wetland region. That's why you have to, treat it specially. But this couple model mostly do larger scale. I don't think they treat the wetland. I don't think we treat the wetland yet. Okay. So if wetland model, you have to coupling. So you have to, because based on the warp model, we had a warp, we include a warp model drive FVCOM once the water becomes wet. Because we had a warp driving for wind model, driving for our coastal flooding model, the tidal flooding model. So we don't have a two-way coupling. But if warp model deep driving the pond when it becomes wet, if it's still dry, they don't give any forcing there. Okay, they don't give it a temperature forcing there. But when it becomes wet, the wolf will give the heat to them. Okay, but they don't have the feedback to how in the land, in the wetland, how to feedback to atmosphere. I don't think Dr. Lee has done that.
No, currently for the land part, because from the wet point into the dry point,
Yeah.
the sea surface temperature is kind of fake. It is just the temperature of the last time when this point is wet. So that is why we do not consider it to be transferred to the atmosphere model. So maybe so in theoretically this is not 100% correct, but currently in practical, because usually the WRF model is roughly at most 1 kilometer resolution. But for the ocean model for FVCOM in the coastal region, sometimes we could be 100-meter resolution or even higher, say 10 or 5 meters. So usually this will not give us any trouble.
You know, when we do the coast inundation model, we do have a heat come from the wharf to the land. Okay, we heat the land, but however, we only when the water becomes wet, we heating. Because water coming, right, the wet, so we get a precipitation, also the heating go into the water. But in this way, we find the problem, so if water too shallow, if you put the really atmospheric heat into the water, wetland region, so you can get a coastal warming, like a hot water, because the atmospheric heat larger because in the wetland, the dynamics is completely different. Right? The circle engine, the sediment, all things there. No, we don't include those things in our model. That's why, if you put the heat into the land, you get into trouble. That's why we assume most of the temperature come out the land water come from advection. Just because water coming from estuary go to wetland region, that's the temperature, how much temperature they conservative go moving there. But we don't put a direct heating on the land. If we can turn on, we turn on it before, then we find a problem. But now we just only turn on the kind of precipitation, because for sea level, we turn on precipitation, put the water in, and the rain, the water get the water in there, but we didn't put the heat budget in. Right? If you don't heat budget, we had to cover whole wetland, like a salt, mud, like sediment mud, whole system in there. Then you can do that. Otherwise, you can go to overheating and overcooling. Right? So that's the reason, some people use that FVCOM model. You use in the Mississippi River. They try to do the model. They turn on the heat budget in the wetland. So in the winter time they get over cold. The summer they get overheat. All the wetlands like blue and red. They call me. I told them, because you don't have a sinking. You don't have a sink. You don't have salt. When the winter time, land was warm, give the heat. Right? Summertime, the land was had a circular and sort of heat, but you don't have too magnesium. That's why you get overheat or overcold. It's not surprising. You can turn on, but I think it's Dr. Lee's coding. He didn't put it. He don't make a turn on this kind of electricity exchange in the wetland. If I said it wrong, so Dr. Lee can correct me. Okay.
Yeah, that is correct. So after FVCOM version 4.4.5, so we added the critical depth to control the short wave and other heat flux.
Yeah. So we should be able to remove that if we get a basic amount of flux out.
Yes.
Like we get a soil water temperature for other, right?
Mm-hmm.
We had to
Yes.
do that,
Mm-hmm.
Ask NOAA give me the funding to do that. NOAA did not give to me money. I think if you apply the ocean model to estuary, you have to include a lot of hydrology and estuary, hydrology system into estuary. Make sure the heat budget is correct. This is a critical issue. I mentioned many times to them, I don't think the ocean people understand. They say, oh, we don't care about estuary. Okay. Yeah, go ahead. Second question. Sorry, I just stop you. Add more detail.
So the second question, still from Yunji. So the question is about why is it necessary to adjust the initial condition of FVCOM using data from WRF? Okay, so when we use the ESMF structure to do the coupling of different models such as FVCOM or WOF, the ESMF lets users to first divide one model into three main parts. So in detail, the first let me find a pen. Okay, so first initialize, then run, then finalize. So if you want to do the coupling using ESMF, you have to first divide the model into three parts. So so how do we divide the three parts? The main idea is to find the do loop. So all the part before the loop do loop is called initialize, and all the part after the do loop is called the finalize. So after we divided the three parts, so we need to know what is the purpose of each part. So for the initialized part, the main idea is to just set up the model. For example, to give an initial condition for the model. So for example, for FVCOM, if you want to do a simulation of the temperature, so you need to first give an initial condition because there is a temperature local term in the NF equation. So in FVCOM, you can either give the temperature initial condition by read it from the restart file or read it from the TS initial file, or just set it as a constant number, for example, 20 degree for the whole domain, right? So here we did the same thing for the coupling model. So when we couple FVCOM and the WOF together, we also need to give the initial condition for all the other variables. For example, there are totally 4 groups of variables from WOF to FVCOM, including the heat flux, evaporation precipitation, air pressure, and the wind stress. So for all these 4 groups, you all need to give the initial conditions. So that is why here we included a part for the phase 3 to just do it after the coupler, which all the variables exchanging with each other. And the same thing happens in WOF. So when before WOF running the main loop, it also needs an initial condition of the SST. So that is why here we also need to transfer the SST from the ocean part to the WOF part. So that is why we need to include the initialized part. So did I answer your question?
No, I can add something here.
Yes, please.
You know, here it's not adjusted, it's set up. No, your question is why you necessarily adjust the initial condition. It's not adjusted, it's set up. No, just because you know the model, you have to in the initial condition, both for WOF and the FVCOM, that Dr. Lee said. I don't want to get more. I just said your question, you will understand it. You said that it's adjusted. No, it's not adjusted the initial condition. It's set up. That's configured. Okay, that's called initialize. Okay, condition, just put initial condition. You run a FVCOM, run WOF, you need the initial condition, right? That's just for this one, but not adjusted the initial condition. Not means you already have initial condition, you make adjustment. No, it's not the case. It's just set up. I don't want to add more. I think Dr. Lee already gave a clear explanation. I just try to clarify the wording. Okay.
Yeah, thank you.
Okay.
It means that initial condition I set up in FVCOM run NMFI didn't change by the WOF data. It just add some air pressure, something like the data from WOF. Is
Yes,
it right?
that's right.
Oh, okay.
So,
Thank you.
For example, let's take the heat flux as an example. So, for the coupling model, WOF will give both short wave and the net heat flux to the FVCOM model. So if we, for example, if we remove this part, we do not transfer the data from WRF to FVCOM, then because the net heat flux and the shortwave radiation is not set up, that means they are all zero. So sometimes it might be right. For example, during in the night, the shortwave radiation is zero because there is no sunshine, right? But however, usually the net heat flux is not zero. So that is why it is important to transfer it from WRF to FECOM.
Mhm. Okay. So you can go to question 3.
This one is from
This is talk about
Jimmy Sue.
Bister and okay Emmanuel, the equation. So I can answer the question. I can talk something about this. Okay, yeah. So this question comes from a theoretical work for Bister and Emmanuel. Considered about a stone. So later the question later talk about a cold weight. That's correct. That's a two different kind of mechanism. So Kerry Emanuel was talking about here. They're talking about for example, if you had a kind of equatorial region when a hurricane was formed, so that's the warm temperature, always can have a more strongly hurricane. Okay, but then later one, I think it's question 4, talking about a cold wake issue. That's what happened with a locally changed scale, but that's what's called a background scale. Okay, if you're a hurricane, come here a lot. That's why it's a lot of misleading. I think Dr. Lee's people describe clear about this. If you only consider Carnot theory, right? So if your air temperature difference is bigger, the gradient is bigger, you can cause like a energy transfer bigger, right? Then that's way here, you can get a more stronger storm. Okay, so that's why you look like ST and the air surface temperature and also the air temperature difference. That's the key issue to drive it to maximum wind. You can estimate how strongly kind of hurricane you have in the starting point, initial point. Just when you form a hurricane and what's on the equatorial region, so if air temperature is difference larger, the hurricane intensity can be stronger. Okay, that means that's the reason you get a conclusion said you get a warm temperature, the warming can cause a more strongly kind of storm. Okay, that's what series try to mean. This is a come out. This series come out is a kind of quantum theory. But quantum theory said, if you had some kind of, if you had energy, right? If you had a maximum efficiency, the engine, your most efficiency, that's efficiency will be proportional to, your temperature difference, right? This is the fourth equation here, right? The fourth equation here, you see that's the fourth things like equation, like you have here. You see that's the temperature, the difference, that's which H, So this is absolute temperature, for cold hot water. If you had a cold water, hot water in the one box, for example, one volume there. So if the temperature difference so big, so then the energy, the efficiency can be strongly. Okay, so this theory they can look about an atmosphere ocean look like a Carnot theory. Carnot theory not just like the system had a two temperature difference, right? But easily for atmosphere ocean also look about a Carnot theory. right? You know, so whole system. So air temperature and the water temperature difference, if you're a bigger one, you can cost more energy. Okay, that's the same thing. But that's only for the larger scale plant. You know, you have systems there. So if the temperature is strong, you can cause a more stronger storm. But doesn't mean, okay, you know, you're locally warming. You know, doesn't if based on this theory, say if you're locally cooling, okay, you go locally cooling because a mixing called the cooling, the storm should be becomes weak, right? No, that's a completely different theory. That's called a background mixing. That was a background temperature structure. In the background temperature and the air temperature difference bigger, you can get more energy, you can create a more strongly storm. But when storm form, they move to north. The storm was formed, they move north. So then the local air interaction beneath the storm can be really affect the intensity because it causes asymmetric grading, you know, heat budget for flux casing. That's a different kind of physical mechanism. Right? That's why you see equation estimate the tropic intensity, tropic storm, but you see only consider air temperature, right? Now this is results can improve significantly if we replace the, you know, you see there's what is the temperature, what it is with the depth average temperature, you know, certain mixed layer, you know, that's a very easy question about this one, because the mixed layer temperature theoretically mixed temperature should be same as surface temperature. You're mixing, right? You see it? If you water mixing, right? You know, temperature should be same, okay, as like surface temperature. ST data just represent for mixed layer temperature, supposedly, but not exactly what is similar. Otherwise, you don't have a mixed layer, mean, right? So then the atmosphere, the ocean heat exchanges only at the sea surface. So you said if I use the average temperature and the mixed layer, yeah, you know, theoretically, temperature, the mixed layer temperature should equal to sea surface temperature, but really what they could be different. They could be different, right? In the real world part, your mixed layer temperature can a little bit grading, but that's depend on how you define a mixed layer. The mixed layer really you know, selected definition for mixed layer is what temperature vertically mix it. Right? So that's why sea surface temperature and the mixed layer temperature should be same. But in the real world, you go to that, it depends on how you define the temperature, define the mixed layer temperature. But you very hard to find exactly same temperature vertically. You have some little bit grading. But this grading should be very small. That's why you don't necessarily to have you can define the ST mixed layer depth, mixed layer ST temperature, your ST temperature is no much big difference. Okay. Any last answer your question? Dr. Lee, you want to add something?
No, I think your answer is great.
Yeah. Okay. Yeah, this one, Dr. Lee, you can answer for that.
So, why does the inertial resonance occur more readily on the right side of a storm? Okay, so for the first one, all this question is discussed on the northern hemisphere. So if we on the southern hemisphere, so everything is opposite. So on the northern hemisphere for hurricane, the wind rotated anti-clockwise, so which means which means the hurricane will the wind will rotate it in this way. So when we consider this question, so let's to make it simple, we just consider three locations. So first, the hurricane center is here. The second location is here, and finally, for example, the hurricane move to here. So for a person who stand on this fixed location, for example here, it is on the right side of a hurricane track. So the hurricane moves from this moves in this direction. Okay, so when the hurricane is here, because the wind rotated anti-clockwise, so we can imagine that for this point, the wind direction is roughly this way, right? And when the hurricane moves northward to this one, and we can imagine the wind is in this direction. So here we can see the wind speed on the fixed location turns to this one. And if the hurricane continue moves northward to here, so because the hurricane still rotated in this direction, so we can imagine for the fixed location, the wind direction is roughly this one. So after the hurricane moves across this fixed location, so we can find that the wind first in this direction, then in this direction, and finally in this direction. So we can see it's rotated clockwise at this fixed location. So in this way, we can just consider its frequency. So I just found a figure from our paper. So I think this one might be make a better description. So first,
No, I think you don't need to go just look about the ideal case first. You know, you know, better describe then what the resistance mean. Okay.
okay. So
Yeah.
for the inertial resonance, so it means that when the wind rotated in a certain frequency, when if the frequency is close to the Coriolis frequency, then the resonance can be occur. So it means that it will the wind rotated in at a frequency that is close to or equal to the Coriolis frequency. So this will makes the ocean rotate in a stronger way.
No, you look at this picture here, this equation. Okay, if you state like a point like L, R, the left side and the right side. So when a hurricane passes away here, in right side, the wind was, for you, the person stay there. You find the wind like Dr. Lee was explaining, this why wind was moving clockwise. Then in the left side, you find the winds moving, anti-clockwise. So initial condition, initial oscillation, necessary condition, the rotation must be rotated clockwise. So if this since rotated anti-clockwise, not counterclockwise, no initial frequency, because Coriolis force always keeps things moving on the right. Right? Coriolis force. So then if you moving here, you move to here, Coriolis always move to right. And northern hemisphere, the motion should be for initial motion, they're moving clockwise. In this way, it's a counterclockwise. That's why it's very hard to get the initial, like a resistance. But however, because in the locally, even without a hurricane, you had a local initial period. It's called 1 over F. F is a Coriolis parameterization. That's the initial period. But then your typhoon, the hurricane moving across there, you cause the wind moving around is clockwise. If the stone was moving certain speed, not every stone can have this, right? When the wind rotated one circle, the period, the time is close to initial oscillation, you call the resistance. Understand that? So if every ocean, without any forcing. Every location, the ocean can be rotated because Earth's rotation, they can rotate it clockwise. It's called inertial motion. Right? This period is 1 over the F. You know, for example, in a 30 degrees north, that's almost 12 hours. Right? So like we are reaching like a 42 degree, so most like a 17 hour. I don't know Korea what the latitude is, depends on latitude, right? So this inertial period is ocean inertial period. That's what happened no matter what your motion now. Once the Earth rotated, you always have this kind of period. If the wind, the hurricane pass, if your location and the wind was moving at same period, same frequency. So this frequency, the same a local initial frequency, they can cause resistance. Okay, that's the reason you can have a resistance, but it only happen possible on the right side because the wind was rotated clockwise in the right side. But left side, because the wind is rotated anti-clockwise. That's a left side impossible to have a resonance, only on the right side. But this, like Dr. Lee said, that's only for northern hemisphere. The southern hemisphere is the opposite. Right? If it's southern hemisphere, collision force make the motion turn to left. You see what I mean? Right? That's why, the inertial motion in the southern hemisphere is moving not clockwise, it's anti-clockwise. Okay, that's different. We talk about the northern hemisphere here. Okay, that's the answer to the question said why you have only have the right side, not on the left side. That's the reason. So then you said why do you expect a strong outwarding? Yeah, if you have a resistance, initial oscillation strongly, you should get a more stronger outwarding. Like Dr. Lee paper showed that. Okay. That's what happened. So later, Dr. Lee can show the paper, but this is physical magnetism. This cartoon show you very clearly why you have one side, not another side, because one is clockwise rotating, we call it anti-cyclonic rotation, and not cyclonic rotation. Cyclonic rotation has no crossfall. The reason because I told you very easy for you can have vorticity. If inertial motion moving like a clockwise, if the wind moving cyclonic like this way, so this vorticity cancel each other, right? But once it go this way, once it go another way, so the inertial motion try to moving clockwise, right? But wind driving the motion moving anti-clockwise, this way they cancel each other. Then you have no energy transfer cause that kind of resistance. Even can dampen your initial oscillation. But then the current initial oscillation moving the clockwise, so your wind also moving the clockwise. If both periods the same, then they get resistance. Right? Just like some kind of bridge. You know the bridge? The bridge, right? You know the bridge? If the bridge had an initial frequency oscillation, okay? So if you have a truck moving on a bridge, you have a lot of truck moving at the same time, and it was on one bridge. You get a frequency cause the truck do the frequency same as the bridge oscillation. The bridge can cause resonance. Bridge can be broken. Right? So that's what happened was that's not happened. This is a couple years ago. You notice China had the most longest river, the longest bridge from Hong Kong to Zhuhai. Hong Kong to Zhuhai, very long bridge. Right? So they built a very long bridge there. So one day, when the wind blew on there, not a hurricane, wind blew on there, they found that the whole bridge oscillated. Okay? because this wind is, the frequency the wind blow, same as the bridge oscillation. They make the bridge oscillating. So there are a lot of people was, a lot of newspaper, TV said probably bridge can be broken down, can be crushed. But luckily that's not happen. Right, so then there was after this one, they do a lot of testing. They put something around there, make sure this is not a resonance. They want to change the frequency of the river, the bridge. Make sure there's oscillation. When the wind come here, it's not a cause this problem again. But time's just moving. Right? If you was on the bridge, it was very dangerous. Drive there. You're not gonna go to the wave, Right? The oscillation like this. Okay. Do we answer your question? I think what Dr. Lee just showed the picture, we blocked it. He show you if you can draw the same picture like Dr. Lee draw. You can see the location there. See how you look like a rotation clockwise and anti-clockwise. Okay. Now, Dr. Lee, you can go ahead talk your paper picture.
Thank you, Dr. Chen. So I want to show this figure from our papers. So here we select the two transects. So you may just see the first one. So this is on the left side of the hurricane. This is on the right side of the hurricane. So during the hurricane passes by the fixed location on the left, on the right, we draw the time series of the wind direction in blue color and the frequency in the red color. So we can see that first, as we discussed on the left, the wind direction rotated anti-clockwise. You can see it decrease. And on the right, the wind rotates clockwise. And the second thing is about the red line. You can see on the left side, the red line, it is always lower than the dashed line. So for this dashed line, it is a Coriolis frequency at our latitude, roughly 40 degree north. You can see on the left, the frequency is always lower than the Coriolis frequency. But however, on the right side,
Dr. Lee, don't say the Coriolis in the frequency. It's inertial frequency.
Oh, okay, thank
It's
you.
not a Coriolis. Coriolis no frequency. Okay, Coriolis force. So
Okay.
inertial frequency. Okay, yeah.
Okay, initial frequency. So, but however, on the right side, at the beginning, it is lower. But when the hurricane pass by and shortly after it pass by, we can notice this part. You can see during this period, the frequency at this fixed location is close to or similar to the initial frequency. So that is when the renaissance happens. So I just want to mention this figure. So if we select another section and the same phenomenon happens, so it is also roughly close to when the hurricane passed by. So during this period, the mixing could be much more stronger than the other period.
Yeah, that's the picture on the left side, right? He was divided by the F. No, frequency divided by F, right? That means then the T frequency equal to the initial period equal to 1. This picture here, that's one. That's one. You draw the picture. This one, this here is the frequency divided by F. Right? If frequency equal to F equal to 1, right? You see here, right? That's if we reach the 1, that's frequency this frequency you have, right? It's equal to the initial frequency. Right? Okay. That's good. Yeah, that picture is very useful. Okay.
So next question.
So yeah. Yes, so probably you can answer the question.
I understand how the cold wave affects the storm intensity, but how does it affect the prediction of the storm track? Okay, so I try to answer it. So first about the storm track. So when we have the observation of the model results, so how we define the storm track, usually we will first find the storm center. The storm center is usually defined as the minimum of the location with the minimum sea level pressure. So when you got all the variables like temperature, air pressure, humidity, all the water vapor, so the first thing you need to use all these variables to calculate the sea level pressure, which means that you will get the pressure onto the height of the sea level. So after that, you can get the distribution of the sea level pressure, and the minimum should be the storm center. And with the time changing, all the locations of the storm center is the storm track. So here it comes to a question that if we want to make a good prediction of the storm track, so we need to do a good simulation for all the variables, including the temperature, the air pressure, and the humidity. And one important thing is the temperature. So if the uh, uh, if the ocean part is not considered, so we see usually the from the ocean part, the surface temperature is, for example, keep the same as the original WRF did. So there is no cold wave in considered. So in that way, it could make the latent heat flux and latent heat flux underestimate. So in that case, the hurricane during the simulation, the hurricane could gain less energy from the ocean. So this will make the hurricane intensity less powerful. So in that way, it will make the simulation worse. So that is why we need to consider the effect of the cold wave.
Yeah. Now I can add something. I can bring the additional way to this way. I think Dr. Lee will show you what a basic, like what a key issue. Now you want to compare two equations, like I mentioned here, like Kerry Emanuel, his student do the paper, equation on the left side. That's only for the climatology condition. That's why if you have a warm temperature, you get a strongly AC temperature difference, so you can get a strongly hurricane, created, then the wind. But they don't. Yeah, you are correct. They did not consider the cold wave in this process. They only consider, because they said if you have a atmosphere, if atmosphere and ocean, the temperature is the same, you don't have a hurricane. Right? Because if no LC temperature, because you get a temperature salinity, air temperature and all temperature so large different, they look like a Carnot system. Then you get a lot of energy exchanges. Right? So this air can get more exchanges because of air temperature. They are not for, it's not only for AC temperature, also energy. Energy also different. Right? So this way you can get like a more stronger hurricane. But a cold wave is different mechanism for this. Cold wave, just like if you look hurricane moving, so if you can get no mixing or something happen, so cold wave can bring the water cold water in the surface. When the cold water surface, they can increase the temperature, LC temperature difference locally within the hurricane. But this increasing can be changed a couple of important things. One is the humidity, right? Humidity was inside the inside the hurricane, so make it a more asymmetric structure. Because when you hurricane like a cylinder, if you one side, for example, the right side have more upwelling, over there, as more cold water, left side no have, no matter what the size is, you can make a special local special temperature, acid temperature difference becomes bigger. So then you can get a more heat budget will transfer from ocean, like Dr. Lee said, like most of the lantern heat budget. But lantern heat budget related to what Weber, right? Because you get an acid temperature difference, you get humidity was inside the hurricanes different, especially. This can transfer more energy to the hurricane, intensify the hurricane. You can talk two things. That's why it was mentioned. That's why if you change the density, air density, the air density can directly relate to the air pressure. Then drop the air pressure center can be more low pressure, redundant pressure, they may intensify the hurricane. All right. Another issue is how can the track. Most of the track will depend on how asymmetric the hurricane is. If a hurricane, all the wind was uniform around the whole hurricane not move. All right? The hurricane, because you're asymmetrically like a spell, the strongly hurricane can really move. That's the reason this not only affect like intensity, also affect the trajectory. But most certain changes the acid temperature difference, the change the lantern heat flux. In the Lee's paper talk about in the cold pool, cold wave can significantly enhance the lantern heat flux transfer from ocean to atmosphere. Right? So ocean to atmosphere. You get more energy to hurricane, make a hurricane intensify. That's discussed from the energy part. From density part, you also make the air density different, right? But density was related to the humidity, right? Humidity related to the kind of air temperature. But both changes, the pressure can changes. Then pressure changes, the hurricane can change its intensity. Okay. Right? I think they had an equation show that, so like I think Lee paper include equation. I think for your first paper you show that.
Yeah.
Not for second paper, right?
Well, I think in the lecture, I remember it includes here.
Yeah. You see, if you change the air temperature, you change the what Weber, flux, right? Over here, so you can change you can change the pressure. That's the whole answer was here. So why they can intensify? Stronger wind causes mixing causes the cooling the sea surface, then increase the lantern loose, ocean loose. Okay, that means get into atmosphere, the air temperature can drop, get the pressure drop. Also, this system I didn't mention here also include the water web, right? Also changes. Okay. We answered all questions. I have 2 minutes left. Any other question?
Yeah, of course. So I want to thank Dr. Chen and Dr. Lee for whole semester of the lectures. Yeah, I my question is I'm still trying to go over all the material, and then do you know how long will the materials be available for us?
So what kind of materials are available? You mean so what type of material?
And the course on through the canvas, the
Oh, the course should be online, right?
yeah. I mean,
Oh,
how long will we still have access to those
That's you should be able to access the material, right? You can download the materials.
okay.
You can go the course website. They get all PowerPoint file. They get 3 version, English, Japanese, and Korea, Chinese, 4 version. So you can download it for PDF file. You also can download PDF file.
Okay. So when will this system close? So this
Oh, this is close. I think it's a May. Oh, yes, good question. 17, can you check for that? I think May
Yeah,
15. I think May 15.
let me,
I think after May 15, you're not able to access it anymore. That's
So
why if you want to download, you should download it before that.
in
yeah,
about
that is a good question. I'm not sure either. So
No,
here,
you know, you can open, you can open one file, see what we set up,
okay,
the date, what the access date. I'm pretty sure we get an access date all sent. You go down, no, you go to your course website available. I think it's May 15, I think. You go to you go to your account, and probably you can see that.
from my side, it is,
No, that's the lecture for day, but the material is available. Materials available. You open each form folder, they say the materials available.
let me check.
Yeah. Go down. Probably you
For
don't.
this, yeah, I don't have the access.
Well, I have information, so I think this is most like a May 15, if I remember this.
so that
Yeah, yeah, May 15.
there'll be
After May 15, not able to access it anymore.
okay.
Okay,
And
but of course, the lecture I showed a day, but they have the materials available. You open a lecture text. Okay, for example, you open this one here. You want to see what day is available? Okay, go down. Go down. Oh, they didn't show that. Okay.
Yeah, on my side there's
I
no.
think it's May 15, if I remember correctly. It's the last day for class.
okay.
Yeah, you see here.
Oh, here.
Oh, May
So
11.
May 11.
Okay.
So
So-
there are still more than 2 weeks. So
And 2 weeks. Yeah, if you can go to not take a long time to download. Okay.
Yeah. And will the discussion boards there be answered before that, or we just
Yeah, this one is you can download too. You can go to board, discussion board. Okay, this one should be available until when class close, university close, not we close.
can we continue to discuss over there until the end, or we just if I have a question to
So the discussion board will only be here until May 11th. After that, I think it will be closed.
Yeah, we should. But now I think it's for regular class, like a Thursday class. Today is the last one, right?
Okay.
Yes. So this semester ends
If you have a
on
question,
Sunday.
if you have a question, you probably you need to send an email.
Okay.
Because we don't access the web, web anymore because we probably like a class every week we check. If without we after this week we not check anymore.
Okay.
That's why you can send an email to us.
Okay. Thank you.
Yeah.
Mhm.
Hopefully this course is that's useful for you.
Yeah, it's a very useful. Yeah, I learned a lot, and yeah, I want to thanks again to Dr. Chen.
So this is like a student, like a no. Also, I think good things we had an evaluation side. You can go to give some evaluation. Okay, all right.
Yeah, help us to improve.
So then we can encourage more students in the future to take the course. We also can improve the course in the future. In the future, So next month, the Dr. Lee and I were teaching for the kind of this kind of GIS course.
Oh.
Very useful GIS course because most of the U.S. government everything you use the kind of GIS system. So kind of so you go to government the picture database with GIS, right? So that's why university we had one professor offer the course for many years. He retired.
Oh.
Then I
So-
was
Do you use the ArcGIS or
we use the ArcGIS book.
Mhm.
I just follow the book over there. So now I was go slow that I want to do myself my whole things.
Mhm.
I go to chapter, get a chapter. Hopefully before summer I can finish it. So then Dr. Lee and I will go to teaching. I will teaching the first a couple 2 years later on. Dr. Lee will teach the course. Right, because this course had a more student interesting because a lot of people want to get a job, they want to learn that. Well, most time we get I think more than 20 students.
Wow.
Sometimes they get last one you get a 40.
Wow, that's a lot.
Yeah, we don't want a 40 student. We only want to have about a 10.
Yeah, too many.
That's why I think we cut the minimum like a 25. We don't want to get too many. Yeah. Okay, good. If no any question, we can wrap us. Thank you everyone that take the course. Okay, if
Yes,
you have any question, you can send an email direct to Dr. Lee. Okay, so I think he can answer your question, help you solve the problem. Okay.
yeah.
Good.
So thank you so much for everyone joining this this discussion and all the discussions, all the lectures of this semester. We really appreciate, and all of you have raised many exciting questions which helped us improve our model and also give us some new ideas of how we understand the ocean, the atmosphere. We really appreciate. And as Dr. Chen mentioned, so if you have any questions about the model, about the physical oceanography, so please feel free to send us email or raise questions on our FVCOM GitHub website. So we'll always be here to discuss to improve FVCOM. Yeah, thank you so much.
Thank you.
Thank
Okay,
you.
bye.
Goodbye.
You.